Imagine a world where things just vanished or appeared out of nowhere. A world where energy could be created from nothing or simply disappear without a trace. Sounds chaotic, right? Thankfully, our universe operates on a much more predictable and fundamental set of rules: the conservation laws. These aren't just abstract scientific concepts. They are the bedrock of reality, governing everything from the smallest subatomic particles to the grandest galaxies. Understanding them unlocks a deeper appreciation for how the universe works and why things behave the way they do. At their core, conservation laws state that certain measurable properties of an isolated physical system remain constant over time. This means these properties are neither created nor destroyed. They simply transform or transfer from one form or location to another. Think of it like a cosmic accounting system. The total amount of something always balances out, even if it changes hands or appearance. This principle of constancy is incredibly powerful and forms the basis for much of our scientific understanding and technological advancement. Let's start with one of the most intuitive: the law of conservation of mass. This law states that for any system closed to all transfers of matter and energy, the mass of the system must remain constant over time. Mass cannot be created or destroyed. Consider a simple example: burning a log in a fireplace. It seems like the log disappears, turning into ash and smoke. But if you could collect all the ash, soot, and gases released, you would find their total mass exactly equals the original mass of the log plus the oxygen consumed from the air. Nothing is lost, it merely changes form. This principle is fundamental to chemistry. When you mix baking soda and vinegar, a gas is produced, but the total mass of the reactants before the reaction is precisely equal to the total mass of the products afterward. This law underpins all chemical equations and reactions. Perhaps the most famous conservation law is the law of conservation of energy. It states that energy cannot be created or destroyed, only transformed from one form to another. The total amount of energy in an isolated system remains constant. Think about a roller coaster. At the top of the first hill, it has maximum potential energy due to its height. As it descends, this potential energy converts into kinetic energy, the energy of motion. At the bottom, kinetic energy is at its peak. Even as it climbs the next hill, kinetic energy converts back into potential energy. Some energy is lost as heat due to friction and air resistance, but this energy isn't destroyed. It simply dissipates into the surroundings, increasing their thermal energy. The total energy of the roller coaster and its environment remains constant. This law is crucial for understanding everything from power generation to biological processes. Hydroelectric dams convert the potential energy of water into kinetic energy, then into electrical energy. Our bodies convert chemical energy from food into mechanical energy for movement and thermal energy to maintain body temperature. Next, we have the law of conservation of momentum. This law states that in an isolated system, the total momentum remains constant. Momentum is a measure of an object's mass multiplied by its velocity. Imagine two billiard balls colliding on a pool table. Before the collision, each ball has a certain momentum. During the collision, they exert forces on each other, changing their individual momentums. However, the sum of their momentums before the collision is exactly equal to the sum of their momentums after the collision. This principle is vital in understanding collisions, rocket propulsion, and even how a gun recoils when fired. When a rocket expels hot gases downward, the rocket itself gains an equal and opposite momentum upward. This is not about creating momentum, but transferring it within the system. Finally, let's explore the law of conservation of electric charge. This law states that the net electric charge of an isolated system remains constant. Charge cannot be created or destroyed, only transferred. Consider a simple electrical circuit. Electrons flow through wires carrying charge. When a light bulb lights up, it's not creating charge. It's simply using the energy carried by the flowing electrons. The total number of electrons entering one end of a wire segment is equal to the number leaving the other end. This law explains why lightning occurs. Charge builds up in clouds and on the ground, creating a potential difference. When this difference becomes too great, charge is transferred rapidly in a lightning strike, neutralizing the imbalance. The total charge of the cloud-ground system remains constant throughout the process. While mass, energy, momentum, and charge are the most commonly discussed, there are other fundamental conservation laws in physics, such as the conservation of angular momentum, which explains why a spinning ice skater speeds up when she pulls her arms in. There are also conservation laws related to subatomic particles, like the conservation of baryon number and lepton number, which govern particle interactions. These laws are not just theoretical constructs. They are the fundamental rules that allow us to predict the behavior of systems, design technologies, and explore the universe. From building bridges to launching satellites, from understanding chemical reactions to developing new energy sources, conservation laws are at the heart of it all. They are the universe's unbreakable promises, ensuring that certain quantities always balance out. By understanding these profound principles, we gain a clearer picture of the elegant and predictable nature of our cosmos. They are a testament to the underlying order that governs everything we see and experience.